All right. Well, we are now ready to look at the final topic that we're going to be addressing in Module 2, which is managing simulation data. So let's go Advanced Simplest Training Documents to topic 2.3, managing simulation data. And we'll just click on that. And what we'll be looking at in this module is we'll notice that Simplest outputs the simulation data, and each waveform is called a vector. It outputs these simulation data into data groups. So we'll look at where are these data groups stored? How do we manage them? How do we control the size of the data group? And then we'll also look at how you can get additional data in a schematic hierarchy using the .keep statement so that you can add hierarchical data to your data group. All right, so let's go, and we're in our symmetric simplest elements. We'll go to examples in Simplest and the advanced simplest training, module 2. And we're going to start with schematic 2.2 AE, self-oscillating converter. I'll double click on that. All right, and we'll just run the simulation. All right. Okay, so we have the simulation, and you'll notice for this, in this example, we're going to be looking at the magnetizing current in the transformer as reflected to the primary winding. And we're going to be looking at this timer 2. Okay. So right now we're only outputting one vector. All right. And it's going to the waveform viewer. And let's just take a look and notice. So we're going to go to Simulator, Manage Data Groups. Okay. So Simulator, Manage Data Groups. And here we can see that there's 3 data groups, and they're named Simplest Tran 1, Simplest AC 1. So what we asked for was we did a periodic operating point analysis, then we did an AC analysis, then we did the step load transient analysis. And so what we have output from this one simulation is the AC data group, which is a function of frequency on the x-axis and amplitude or phase on the y-axis. And then we have the transient data group, which is a function of time on the x-axis and voltage or current on the y-axis. And so that one simulation generated these 2 data groups. And the transient, so the periodic operating point analysis was a transient, but then that data was overwritten by the step load transient. So this is the step load transient, and then before that was the AC transient. So you'll notice, and I'm going to just make a little adjustment here so it looks like what's in the... So you'll notice that we have what's called the current data group. So that's the last one that was stored. And so if we wanted to look at information in a previous data group, then we would have to change the current and set that. So if I wanted to look at the AC data, for example, and randomly probe those, I would need to set this data group to the current data group. And then that would allow me to do some random probing of that information. Okay. All right. So each data group is completely independent of any other data group. And you'll see as we run more simulations, we'll have, there'll be data group from previous data groups from previous simulations as well as the current one. All right. So where are these data stored? All right, so we'll just cancel out of this. And to do that, to find that, we can go to File, Options, General, or we can click on this little gear icon, which is for options. There's also a simplest options here, but we're going to be in this module, we're just going to be looking at the regular symmetric simplest options. Okay. And you notice we can set up our defaults. Like, for example, I am not a big fan of having the grid show. So I like to hide the grid. So here's where you can set up your favorite options for how you like to manage your schematics. So highly recommend looking into this. But what we want to do now is we want to look at where the default file locations are. So in particular, where do we store the temporary simulation data? And as you can see, it's in this directory right here. Now you could double click on that and set it to a different file location if you wanted to. We found that this default location works quite well. But what we highly recommend that you do not do is don't use a network drive to store your temporary data. You don't want to incur the delays, the potential delays of communicating over a network when you're storing simulation data. That can, it best slow things down, and at worst, you can cause some difficulties in getting all the data from your machine to some local drive. So don't choose a remote drive for your simulation data. Keep it on your local machine for your temp data. Okay. All right. So we talked about changing the data groups. Why would you want to do that? Well, for example, let's suppose that I did the following. And let's just suppose that what I had done was I don't want to do the step load transient. I just want to do pop in AC, and I will say okay here. So you don't have to do this. You can just watch. So now if I run the simulation, so there's my pop analysis. And then we also did an AC analysis. So let's just say, you know what? I want to look at this output voltage. So I want to randomly probe my output voltage. I happen to know, well, I know this isn't, I was looking for a time domain waveform, and I'm looking at a frequency domain waveform. Well, why is that? Well, if we go to simulation, manage data groups, we notice that we did the pop analysis first, then we did the AC analysis. So then if we go here, and let me just shorten this up a little bit. The AC analysis data group is the current data group. If I want to probe the pop information, I need to set it to the current data group. And now if I go back and probe the output voltage, now I see this is what I expected to see. So that's just one example where you may very well need to change the current data group. Okay. All right. So this is temporary data. So if you think about it, you run hundreds of simulations, if not more. If you're working on a project, you're going to run 100 simulations or more in a day. Most of those simulations aren't archival value. You made a mistake. Oh yeah, it's now I want to add this. Now I want to modify that. So you need to manage. So all the data gets stored in this temporary data directory. Now, how long do you keep those data? When do they get deleted? And so this is where you will change that. So if we go to so we want to go to File, Options, General, or we can click on the little thing again. And now we'll go to the Graph Probe Data Analysis tab. And you can see this tab looks a little different than it did in our docs, but it's still got all the same info. So temporary data files, the delete options, all right? So this is what we're looking at here. So when do you want to do that? If I would recommend that you never click the never button, but there may be times when you need to do what you need to do. So if you click this button, this says, hey, don't tell me that you know better than me. I know what I'm doing. Let me do what I need to do. I like to check when the program starts. So what that says is, as I'm running simulations, I'm accumulating more and more temporary data. I'm not going to delete those data groups until I start the program again. So if I close the program, the data's still there, but as soon as I start it up, it disappears. This button will say, okay, I want to delete the data as soon as I close the program. Now, the reason I don't do that is I sometimes just start closing windows. And if I accidentally close my simulation, my application window here, there's many a time when I've closed it and realized, oh no, I wanted to save some of my data. Now, if I'd chosen this option, that data would just be gone. If I'd chosen this option, it's still there, but what I can't do is start up the application again to go find it. So I need to know where I stored it, and then go using my Windows Explorer and go find the data that I want and save it. Okay. Now the most aggressive option, and this is an option where you very well may need to exercise this when you're doing a lot of simulations. So say like you're doing 1,000 Monte Carlo runs or more, or say like you're doing lots and lots of multi-step sweeps, or you're doing DVM and you're just running all day, every day. You may be you don't want to fill up your hard drive before you either close your program or start it up again. So this says when the data is no longer needed, which typically means you keep the last 3 data groups, but then as you simulate the fourth one, you get rid of the first one. Okay. But for most days, most things, when the program starts is a pretty safe option and lets you make a little mistake and still be able to recover. Okay. What determines the size of the data group? So we'll close this. All right. So let's do this. The size of the data group is determined by 2 things. First, how many vectors, how many waveforms are you storing? Right? How many are you keeping during the simulation? And how many data points do you have for each waveform? Or what's the length of each vector? Okay. So those are the 2 things that determine it. So let's first start about how many vectors are in the data group. So if we go to Simulator, choose Analysis, or you can hit the F8 key, we will notice down here we have save options. So you see the save options. If you click all, what that means is you're going to save all of the node voltages and branch currents in the top level schematic. Not everywhere. Not if you have a hierarchical schematic, this option doesn't save everything as you go down the hierarchy. It only is going to save all node voltages and branch currents in the top level schematic. If you click this option, the voltages only, then you will be saving just the node voltages, all the node voltages in the top level schematic. And if you click this option, you will only be saving the fixed probe. So if we look at fixed probes, here's a differential voltage probe. Here's a single-ended voltage probe here. Here's our inline current probe, for example. Okay, so as you get to a very large circuit, very complex circuit, this is typically the option you want. Saving all is going to be, you need to be careful because, again, with power supplies where we have very high switching frequencies and sometimes simulate for many, several thousand, maybe 10,000 switching cycles, like with a PFC, you can fill up your hard drive really fast. And so you want to be very careful about that. Okay. So these options, though, only apply to the top level circuit. And for power supplies, this actually is a good choice. However, if you are creating a schematic, shall we say, that you're creating a schematic that has hierarchy, maybe you're designing the control circuit, the power management IC. So you're just designing what goes inside the IC schematics symbol. Or in this case, we're going to look at, I'm designing the subcircuit for my parameterized opto. Then how do you get data there? Okay. So let's do this. You're going to have to just watch here. You won't be able, if you're using elements, you won't be able to follow along because you won't be able to dive inside of the opto. But let me do this. I'm going to go to the same schematic. Now I'm using the full version. All right. And so now I can double click. Well, I'll highlight the opto, right click, descend hierarchy. You can also do, it's the same as Control E for enter. So we just, first I'm going to have to run a simulation too in the full version. Okay. And now if I want to go in, let's say I want to randomly probe node voltage here. I don't have any fixed probes. I just want to take a look and see what this voltage is. Well, you can see the error message that pops up in the command shell, and it gives us, a number of things. And let me just zoom in here a little bit. So either no simulation has been run, well, we know that's not the case, or the wrong data has been selected. So we're looking at the wrong data group. The current data group's not correct. Well, I know that's not the problem because I want to look at the most recent data group. And so then the other option is the data for that node wasn't saved. Well, that's the problem that I have. I don't have a fixed probe on here. So because it's in the hierarchy, there wasn't a way that Simplest wasn't told, hey, we need to save, some of this information. So how can I do that? Well, if you hit your F11 key and open up the F11 window, and you can do that, either do in the F11 window, or you can just come down and grab this. You will see there is a star.keep space star V. So let's just undo this first asterisk. The asterisk makes the .keep statement into a comment statement. Now we're uncommenting this. And so now we have a command in the F11 window of this subcircuit that says, keep information. And star V means keep all the node voltage information at this level of the hierarchy. Wherever this is encountered at that level, we want to keep this information. Okay, so now if I go back to my schematic, rerun my sim. Okay. And now I drill down into my subcircuit. Now, if I right click, probe voltage, and now I want to choose here. Now you can see this green curve. So now I've actually saved the voltage. In fact, what I did is I saved all the node voltages in this subcircuit. Okay. So this is how you can save hierarchical data, and it's very handy. The keep star V option is very handy when you're debugging a schematic. So you're not going to run long simulations. You're just trying to make sure everything's working. You're not sure what you're going to need to probe, so you want to keep all your options open, right? That works quite well. Once you have a big schematic, you have a complex IC, man, you don't, this is going to cause you issues, okay? So let's just look at this .keep statement, okay? So there's other flavors of .keep. So we just talked about .keep, and then there's a space, star V, and that keeps all the node voltages at this particular hierarchical level, wherever, it happened to be, wherever it was engaged. If I say keep space star V, that means we're going to keep all the node voltages at this hierarchical level, and in every subcircuit that's a child of this subcircuit. Okay. So for example, if I did keep star V at my top level on my top level schematic, that would keep all the node voltages of the entire circuit, all subcircuits, and all the subcircuits of those subcircuits. It would keep all those node voltages. This, like I said, this can be very handy when you are debugging. It can be really dangerous when you're not. So, this is working great. Now I got to run that long simulation, and watch out, because if you have a really big complex circuit, this can fill up your hard drive in a heartbeat. Okay. So if I want to keep currents, branch currents, .keep star I space star I will keep all the branch currents at that one particular level, hierarchical level, that wherever this statement is encountered. Keep space star I will keep all the branch currents at this hierarchical level and lower levels. If I do keep star I and star V, that would be, all right, keep the branch currents at this level and all the node voltages at this level and below. And the nuclear option is keep space star V space star I, and that's going to keep all the branch currents and all the node voltages in the entire system. Okay. So it is not a kind thing to do to send someone else, say, like, I want you to check out my schematic. If I send you that schematic with this statement active, that could, and now that person doesn't know that this option is there. That can lead to some very unpleasant surprises. So you want to handle this with great care, okay? Particularly with power supplies, where we tend to have very high switching frequencies and often want to simulate many switching cycles. Okay. All right. So we've talked about what vectors, what waveforms are going to be saved during a simulation. But now let's talk about, well, how many data points are there going to be per waveform? Okay. And then, so we know that we've talked about the number of waveforms that are going to be in a data group. Now we're going to talk about how many data points are there going to be in each waveform. Okay. So I'm going to go back to my elements and just tidy up a bit. So now you can join back in the fun here. And we're going to look at schematic 2.2 AE, our self-oscillating converter. So we're talking about how many data points are there going to be in each waveform vector. Well, notice, you remember from when we were doing just a bit ago, when we were talking about how to set up a transient, there's a portion where you can say how many data points do you want simplest to output. And in our case, and we'll just verify that. So we go F8 or simulator, choose analysis. We'll go to the transient tab. And you remember that I had unchecked this, so I'm going to check that back. So we have said we want to start saving data at t equals 0. We want to stop saving data at 500 microseconds. And we want to output a total number of 4,000 data points. Okay. So that's what we said. And what this will do, this setting here, it will output 4,000 equally spaced, or very, very nearly equally spaced data points. There may be a little round error, but not much. Okay. So let's do this. Open up your schematic 2. Let's see, I'll close this now. Your 2.2 AE self-oscillating converter, and close your waveform viewer. And now let's run the simulation. Okay. I neglected to, all right, so you will have had this transient portion checked. So I'm going to just redo this real quick. So you need to have, we want to run the transient simulation. Okay. So let's run the simulation. Okay. And now we'll look at the waveform. Okay. And what do we notice here? We notice that it has 5,636 data points. And how did we collect that? Well, one of the cool things, so I'm going to go to my, I'll show you just with the output voltage, for example. If I go to edit, add measurement, I can add any measurement that I might want. And so I can select, and one of the measurements that you can get here is vector length. So I can choose, and that's what we did. So we said, what's the length? So how many data points are there in this vector? And that's how we set up the current probe for our magnetizing current inductor. And so what it's telling me is we have 5,636 data points. But how do I reconcile that with the fact that I only asked for 4,000? Okay. So let's do this. Let's say, all right, so we have a 1,600 data points that are, I can't explain. So now what I'm going to do is say, all right, I only want one data point. So when I say one, I'm going to get one at the beginning and one at the end. Okay. So now we'll run this again. Okay. Run the simulation again. Okay. Pretty much looks the same. But notice, here's that difference. I still have 1,600 and some odd data points. So let me do this. I'm going to highlight the waveform. I'm going to go to curve, show hide points, and let's just take a look. So remember back when we were talking about how to set up a transient, we said this is the information that Simplest needs. It needs to know when is it going to start saving data and when is it going to stop. This is what you want to see. So you said, I want to see one data point at the beginning, one data point at the end. But Simplest has its own agenda. And so it will store data points. It'll be taking data points at every transition from one piecewise linear topology to the next. So where you see this cluster of data points, that's telling you that you're going to, that we're transitioning from, a number of piecewise linear segments. We're transitioning from one to the other here. And you can notice that here. And what Simplest does is every time we go from one piecewise linear segment to the next, it saves a data point at that exact transition moment, and then it saves a data point slightly before it and slightly after it. So every piecewise linear segment actually generates 3 data points. Okay. And the reason that we by default output those is they tend to be at very critical moments in the waveform. So it actually enhances the fidelity of the waveform that you get to see. And let's just take a look at this. And remember, as we're get ready to do that, nothing you put here impacts the accuracy with which the simulation is run. Okay. It always gets to the same point. So Simplest is going to solve all of these critical moments where it transitions from one piecewise linear segment to the other. Whether you want to see the data points or not, it's going to do that. Okay. Okay. So now I'm going to do a quick demo here using the full version because I want to do a quick modification in here. So I'm just going to jump back to the full version. Okay. And so I'm going to do this. So I'm going to go and do the default, right? So I'm going to run this. I'm going to do 3 things in a row. So I'm going to do what we first did. All right, and that has 5,000 data points. Then what I'm going to do is I'm just going to double click this. I'm going to make sure, so I want to see a separate curve, different color for all these simulations. Right now, you'll notice the history depth is 1. I want to override that for this little demo. Okay, so now what am I going to do? I'm going to do what we did earlier. I'm going to go and say, I only want to see 1 data point. So we'll run that. And what we anticipate now is we're going to see just the points that Simplest cares about. All right. And if we look, okay, so now if I select both of these, we do show hide points, we'll see that, okay, in one case, all right, here's my 4,000 equally spaced data points, all right? But you can see that if here, Simplest doesn't, it's not doing anything here, doesn't need to do anything here to get to this point. But it's got a lot of information up here at the peak, which is completely missed with my 4,000 data point spacing, okay? And that's pretty common. And we can see that Well, we're going to come back and just look at and see what the impact of that is. But just to demonstrate the accuracy, if you notice, we come over here, no matter what, both waveforms. So if I hide my green just real quick, both waveforms end up at exactly the same point. So there's nothing that I can do in my setup here that's in terms of what I ask for simplest to output. Nothing is going to change the accuracy of the calculations in the simulation that simplest does. The only thing I'm impacting is what I want to see on the waveform viewer. Okay. Now, there's another feature. It's called no forced output data option, and that's here. Normally, you would leave this unchecked. What that says is that, so the forced data is the data that simplest wants to see. So that's 1,634 points. That simplest outputs every time there's a switching instant. If we say no forced data, then then all of the simplest data that it will calculate, but in this case, it will not output, will be, it won't go to the output, but simplest will still get there. So now we're not going to output any of the simplest data that it keeps and calculates. And we're only going to ask for one data point at the end, and there'll be one at the beginning automatically. So now if I run that, and let's go full scale here. So here's my one data point at the end, at the beginning, my one data point at the end. You said that's all you care about. And so, and I'll just hide these. Okay. Hide those. Okay. So we can see that no matter what we put in our simulation setup for the transient in terms of the number of data points, it doesn't impact the accuracy. All roads are going to lead to Rome right here. There's nothing you can do to make simplest solve its set of equations with less accuracy. It's like we talked about earlier. It's kind of hung up on accuracy. It's going to do its thing. But you do have complete control a lot of control on what you actually see, what gets output to the waveform viewer. So when would be some moments where you actually it'd be a really good idea to exercise this feature of don't output the simplest data. Okay, what would that and there's a couple things. One is if you want to post process the simplest data, let's say I want to do an FFT on a waveform. Well, many of the FFT algorithms require equally spaced data, a fixed time step, equally spaced data, and then you don't want all the extra stuff that simplest wants at every switching instant. So that would be a really good reason why you would click on this. Another option might be there's a really long simulation where there's just thousands and thousands of piecewise linear topologies, and you don't need all the extra data. Okay, so this option is available to you. But let me show you why we, as a default, do not have this checked. Okay, so I'm going to check it, but now I'm going to go back and say, let's go back to our original 4,000 data points. Okay, and yeah, let's just run this again. Okay. All right. So we're going to need to take this waveform and we're going to change the color so that it jumps out at us. And let's make it nice and pink. Okay. And I will also just temporarily hide these other ones. Okay. So this is the resulting waveform that I get with just the equally spaced, my 4,000 equally spaced data points. And you can see that, maybe this is okay, but there's information at these peaks. For example, I can't tell whether my circuit's stable or not with this waveform, right? I would have to have a whole lot more data points to be able to tell that. Whereas if I include the the simplest data points here, then I can see, okay, that looks pretty stable operation right there. Okay. So that's the difference between just the equally spaced data points and then adding in the simplest waveforms, the simplest data points that are stored at these instances where we transition from one piecewise linear topology to another. Okay, so let's just summarize here. We've talked about simplest stores simulation data in data groups. These data groups are stored on your local hard drive, and we highly recommended that you not put them on a network drive. You can change the location where they're stored. The data groups can be archived and reloaded for plotting. Let's just take a quick look at that. So if I have a data group, and so if I know what my, I select, excuse me, if I go and manage the data group, so I pick the one that I want is my current data group. So whatever my current data group is, I can then go to File and Data and Save. And it will then take that the current data group, whatever that is, and I can save it. I can change the name and I can change it to an archive, a place where I want to keep it. All right. And then if later I want to go back and load that data, I would go to Data and then Load, and it would ask me to navigate, to the right place. Okay. So we can store these data groups. We can load them back up. Now, it doesn't save any formatting. So it doesn't save, it just saves the data. It's literally saving the data. If I want to save the graph, then I would save the graph, and then that will save all of my settings. We can use the .keep statements to automatically save data from hierarchical blocks. We talked about that, and you don't have to remember all of these, this syntax. Just remember this is where you go. You go to the managing simulation data section of the training course, and you look this up, and okay, I see that. All right. But you can use that then to store, to save data from, at different hierarchical levels. We talked about the number of points in any waveform is a combination of the number of equally spaced points you asked for and the number of piecewise linear topology changes that there are in the course of that simulation. We talked about the no force data option that allows you to suppress the data points that Simplest generates, and we by default output each time we have a topology change. And then, but we talked about no matter what you do, what you pick for the no force data option or the number of plot points that you ask for, none of those can impact the accuracy of the internal simulation calculations that Simplest does. It goes for max accuracy all the time. But these settings can impact the fidelity of the displayed waveforms. So, for example, if I want to use these waveforms to calculate switching losses, for example, I want very high fidelity waveforms, right? Very high. And so I will ask for a lot of data points per switching cycle, but I just won't ask for very many switching cycles. Okay. But Simplest never compromises on the accuracy of its internal simulation calculations. Okay, so that winds up our topic on how we manage simulation data, and we'll just then move on to our next section.
Thanks, Tom. We had a question come up here a few minutes ago.
Yes, sir.
If I were to accidentally close my waveform viewer, but I want to bring back my last simulation data or waveforms, is there an easy way to do that?
Yes, there is, and you're going to tell me what it is. I remember
Yes.
that. All right, so I did that. Oh no.
Yep.
And
so you will go to Simulator, and then the replot data group.
Oh, look at that. Okay.
So this will bring up any available data groups in its history.
Okay, so
that you can select.
Right. So if I want to go here, I go there. Boom. So.
And then this is good to know too if you use the file data save, if you're saving away a data group and then you load it later on, you can use that same simulator replot data group in order to plot all that that historic information that you have.
Right. Excellent. Perfect. Yes, it's interesting when you get going. It's so easy to okay. All right, good. Then you just oh no, I didn't want to do that. Which is why the options here that we have of when you delete the data, the temp data, that's why I pick when it starts, because that gives me a chance to recover. So, okay. Any other questions, Matt?
I think that's about it.
All right. Excellent. Thank you.